Okay, this is the first video of my part of the lecture series. And the content of my lecture series, well, is actually well described here in this title that we have over here, because of the fact that it says Quantile and distribution regression models. Well, what we should realize is that these are two related topics. Well, you could say regression models. And what you could also say is that they are topics which are relatively recent. Well, that's not completely true because of the fact that quantile regression models already exist for over 40 years. But you should also take into account that the use of quantile regression models is relatively recent. Only in the last 10 to 20 years, people have been using quantile regression models on a more frequent basis. And that is quite different from, say, many other methods that are used in econometrics, especially if you compare it, say, with, for example, ordinary least squares and instrumental variable estimation, which already exist for almost 100 years. At the moment that we're going to look at the distribution regression models, well, these are actually much more recent. Even though there is an original article from 1997, we should realize that the use of distribution regressions is only since 5 to 10 years. So therefore, concluding, I would say that this is a topic that is relatively recent and actually also quite relevant. But before I'm going to really talk about these models that we have over here, maybe it's good to always start with a motivation. I would like to call this an introduction. And what I would like to do here is to start with a very simple model, and that's the linear regression model. I'm pretty sure that you have seen this linear regression model before, and that you have seen many more difficult models than this linear regression model that I have over here. But let's start as simple as possible. So therefore we have here at the left hand side yi, and at the right hand side we have here xi beta plus ui. Well, what we should realize is that we are going to make, as I say here, the standard assumptions. So that means, of course, that we have two important assumptions over here. First of all, that the relationship between our regressors that we have here at the right hand side and our y, that is linear. So we could have expected a lot of ways in which the regressors could have had an impact on y, but among all those possibilities, we are going to only look at a linear regression model. In addition to that, I'm also going to assume here that x and u, well, that is the standard assumption typically made, of course, in a linear regression model, that x and u, they are, say, uncorrelated to each other. And the reason why we typically make these two different assumptions is because of the fact that then it is possible to estimate this model with ordinary least squares, and then the beta coefficients that we are going to have over here can be consistently and unbiasedly estimated. So that is pretty nice. What we should take into account that even though these two assumptions are usually immediately discussed at the moment that you're going to look at a first lecture in econometrics, there is one particular assumption which is also important with respect to this linear regression model that usually gets less of attention, at least in an introductory lecture in econometrics. And that is that, well, we do of course allow for the fact that the outcomes that we have over here at the left hand side are going to be different among individuals that are exactly the same. And the reason behind that is this error term that we have over here. This error term is of course a random component, and it is unobserved, which implies that individuals could have different outcomes with respect to this ui that we have over here, even in the case that they are in fact the same. And that of course also implies that individuals can have different outcomes even in the case that they are observational equivalent. That's the nice thing of this representation that we have over here. But take into account that we cannot say that about the impact that xi has on yi. We should realize that by this model we assume that the impact that xi has on yi must be always the same, say for every individual that we have over here. And the reason behind that is because of the fact that it's always equal to this beta. In order to make that a little bit more clear, let's look at a very simple example. Suppose that the left-hand side of over here is going to be the log hourly wages. And what we would like to do here is that we would like to look at the returns to education. So therefore we are going to have a lot of characteristics of workers here at the right-hand side, including of course indicators with respect to the education level of the individual. But let's now make it as simple as possible. Let's assume that there is only one particular type of education, and that's that you can actually go to college or you cannot go to college. So that means that education can be represented simply by a college dummy, which is equal to 1 in the case that you have been going to college, and it's going to be 0 otherwise. Well, then you should realize that the beta coefficient is then going to give us, say, the return to college, how much you get extra at the moment that you have a college degree. So, as I already said, suppose that this is going to be the log hourly wage. Well, then it's going to be in percentage terms. So that means that if this beta coefficient, for example, is going to be equal to 0.3, so that means actually nothing else is that any individual that we have now in our data set is going to get 30% extra in terms of the hourly wage at the moment that that particular individual goes to college or went to college, compared to the situation in which this individual decided not to go to college. Well, that is of course very restrictive. It could be possible, of course, that there are differences between individuals with respect to the returns to education. Well, true, we can allow for that. We can, in fact, allow for that even in this model that is over here, because of the fact that we can also look at interaction terms. We can interact the college dummy that we have over here, we can interact it with all kinds of additional characteristics that we have, such as the gender, ethnic background, region, age of the particular individual. And then we can allow for the fact that there are differences in terms of the returns to education between individuals, but we should still take into account that what we are going to have is that if individuals are observationally equivalent, then they should also have the same return to education. Well, that is still very restrictive. You should realize that it could be possible that we have two individuals that are observationally equivalent, but that could have different returns to education. Well, I'm going to say more about that on the next slide, but before I'm going to do that, let me first say something about why this is important. Well, the return to education is important because of the fact that in most countries, the government pays actually for university. Even in the Netherlands, we should realize that the government pays more than $1 billion, even a couple of billions for university education. And then it's important to know how much people are going to earn extra at the moment that they go for college. At the moment that we are going to see that there's hardly any difference between individuals that went to college and those that did not go to college in terms of their, say, hourly wages, or maybe better to say, individuals do not increase their, say, wages at all at the moment that they go to college. Well, then it doesn't make that much of sense to pay so much money into higher education. On the other hand, of course, if we are going to see that there is a huge increase in terms of your wage at the moment that you go to college, well, then that's good for the government. For example, it's good for the government because of the fact that, well, then you can levy higher taxes to those individuals that have higher wages. And that is, of course, always a good thing for the government. So therefore, you should realize that it's important for the government to know what the return to education is. But then, of course, we also need good models in order to estimate that impact. And a model that's going to assume that, well, the returns to education is going to be exactly the same for individuals that are observation equivalent is definitely not the correct model. So therefore it might be good to look at another model. Let's look at this model that is over here. Here we have at the left hand side we have yi, and now at the right hand side we have xi times beta ui. This still looks like a very simple model, but we should take into account that this model is actually much more complex than what we had at the previous slide. And the reason behind that is because of the fact that this is a so-called not additively separable model. What does that mean? Well, now in this case you should realize that beta is no longer going to be a coefficient. It's now a function of this ui that we have over here. And that of course implies that at the moment that I'm going to change the ui that we have over here, at the moment I'm going to change my error term, then at that moment in time this beta coefficient is going to change. And that's quite different from what we had on the previous slide. The moment that we're going to look at the previous slide, you should realize that, well, even though we do have, of course, an impact of x on y, and we have an impact of u on y, we should realize that that's completely separated. That is to say that the way in which ui is going to have an impact on yi is completely separated from the way in which xi is going to have an impact on yi. That is to say, at the moment I'm going to change the xi, well then it's relevant to know the beta, but it's irrelevant to know what this ui is. And also here, at the moment that we're going to change the ui, and if we want to know what that has for an impact on this yi that is over here, we're going to see that it's irrelevant what actually this xi is. So therefore, we should realize that, well, here we have a so-called additively separable model. The, say, observed characteristics that we have over here, the regressors that we have over here, well, they have a completely separate impact on yi from, in fact, the unobserved part that we have over here. Well, that's not true in this model that we have over here, because here we do see that at the moment that I'm going to change u, then we do immediately see that that actually is going to affect the way in which x is going to affect y, because of the fact that this beta is going to change at the moment that I'm going to change u. Therefore, this model is quite more complex than the model that we had at the previous slide. By the way, I haven't said that yet, but this is usually called the random coefficients model. So this model is much more complex than the model that we had at the previous slide, but as we will see, it's also, well, much more realistic than the model that we had at the previous slide. But before I'm going to say anything about that, I have to say something here in addition, and that's about, you could say, identification. What we should realize is that at the moment that I'm going to change the distribution of this ui that we have over here, then I can always, say, rewrite beta in such a way that I get the observationally equivalent model. That's another way of saying that actually the distribution of ui, or you could say the function beta that we have over here, they are actually not separately identified. So therefore we have to use a normalization over here. We have to make an assumption with respect to either the, say, function beta that we have over here, or the distribution of ui that we have over there. But we're going to do the last. We're going to make an assumption with respect to ui, and at the moment that we can decide ourselves about which distribution we're going to use, well then it's always best to use a very simple distribution function, and therefore I'm going to use here the standard uniform distribution function between 0 and 1. So I'm always going to assume, and that's actually without loss of generality, that the distribution of ui is going to be standard uniform. Now let's look at a very simple example. Suppose that we have, again, that we are going to look at the returns to education, and we here at the left hand side we have the log hourly wage, and on the right hand side I'm just going to introduce a college dummy. Of course I can take many more things into account, but here for this very simple example, I'm just going to assume that, well, there is just one particular thing that is going to have an impact on this wage that we have over here, and that is that S that we have over here. At least only one, say, component that we can observe. So S, again, is going to be a college dummy. It's equal to 1 in the case that somebody has a college degree, and 0 otherwise. Well, in this case, we should realize that based on this model that we have over here, and even in the case that we are going to assume that schooling is exogenous, that's generally of course not true, but even in that case, we should realize that individuals, based on this model that we have over here, individuals with, say, that we are going to have in this data set that we have over here, in this model that we have over here, could have different returns to education. And that is of course possible. It is possible that some individuals have a higher return to education than other individuals. Let's look at a particular example. Usually it's based on the talents that individuals have. So suppose that we have a particular individual that has very good talents to become a good surgeon. So in this particular case, that means that you have, say, particular kind of talents with which you are born. It's not that you actually got the, well, you went to med school and therefore you're now a good surgeon. Some individuals are simply better surgeons than others because of the fact that they have particular kind of talents with which they are born. So let's now look at an individual that actually has these good talents with respect to becoming a surgeon. You should realize that you can only become a surgeon in most countries at the moment that you went to med school. And that means, of course, that this individual can only get essentially the high wages that he or she is able to receive at the moment that you're going to be a surgeon by going to med school. And that means, of course, that this particular individual actually has a very high return to education because of the fact that if that particular individual's not going to med school, well, then that particular individual could, of course, do something else, not become a surgeon, but it's going to be very unlikely that the talents that that particular individual has are going to be used in exactly the same way at the moment that you decide to become something else. Say, for example, a carpenter or an accountant or something like that. So therefore we should realize that for this particular individual, the returns to education, of course, are going to be quite high. But that might not always be true for any individual. And that's not because of the fact that not everybody is able to go to college or able to finish college. But particular individuals may have other kinds of talents, and it may be possible that these kind of talents, even though you can get a high wage with it, do not require a college education. My favorite example is always soccer players. If you're going to look at a soccer player, let's look at a very good soccer player. I'm not that much into soccer myself, but and I do know that the example now becomes a little bit old, but let's look at somebody called Messi. Well, he now actually works at Paris Saint-Germain, and we do know that well, he has a relatively high wage. His wage is probably higher in a couple of weeks' time than I actually get in my whole lifetime. So he has an extremely high wage, but most likely his returns to education are going to be quite low. And that's not because of the fact that he would not be able to, say, finish college at the moment that he's going to go for college. That's not the issue here. The issue is here that he already received such a high wage, even without going to college, to play at Paris Saint-Germain. He doesn't need a college degree, so therefore he's not going to increase his wage at the moment that he decides, for example, to go for, say, Harvard Med School or something like that. He doesn't have to do that. If anything, his wage will actually be lower at the moment that he decides to go for university than at the moment that he decides not to go to university, because of the fact that then for a particular moment in time he's not able to play soccer. He would probably, if he had done that a couple of years ago, he would probably not have received all the say, premiums and all the things that he actually has won in the last couple of, say, 10 to 15 years. So therefore, his returns to education, well, it's negative, probably, if anything, and it could be actually quite negative. So therefore, we see now, this is two quite extreme examples, of course, but we do see that it is possible that individuals are going to have different returns to education. So therefore, this model that we have over here is much more realistic than the model that we had at the previous slide. Well, you should realize that this is related to something that we typically call treatment evaluation. Also, in a treatment evaluation literature, people realize that it is important to take into account, say, heterogeneous impacts. Well, I'm pretty sure that you have seen treatment evaluation before, but I'm going to start here just simply from, say, scratch, and what I'm going to do is that I'm going to introduce here an outcome variable, this yi that we're over here. This is typically called the, say, outcome model or the causal outcome model, sometimes called the Rubin causal outcome model. And yi can have two different outcomes. It is either equal to yi1, in the case that another random variable si is equal to 1, and it's equal to yi0 at the moment that si is equal to 0. Well, now you should realize that this immediately gives us a problem. And the reason behind that is because of the fact that we should immediately realize that we can only observe one of the two. We either observe yi1, in the case that si is equal to 1, because of the fact that we do observe si, and at that moment in time, we do know that our yi that we observe must be equal to yi1. However, in that particular situation, we're not going to be able to observe yi0 because of the fact that if we do observe yi1, then yi0 is not observed because of the fact that then si is equal to 1, so si is then not equal to 0. On the other hand, at the moment that we are going to have that si is equal to 0, then we do observe yi0, and we do know that that is what we actually observe here with respect to yi, but we have no idea about yi1. Take into account that this is actually the situation that we have in many, well, say, practical treatment evaluations. The treatment evaluation literature is usually called treatment evaluation because of the fact that it's tightly related to medical treatment. Suppose that we're going to look here at a set of patients that have a particular kind of illness. And what we're going to do is that we're going to give at least a part of these individuals are going to receive a treatment. So si equal to 1 here means that individuals are going to receive medical treatment. And after that, after say a couple of weeks or months after these individuals have received either a treatment or not, we're going to observe the health status of these particular individuals. So that could be anything. It could be a very general, say, indicator of health. It could be more specific with respect to the specific illness that we have. We can, for example, have here yi just as an indicator whether you have completely recovered from your illness or not. Or it could be as bad that this yi simply is an indicator whether you're still alive or not after, say, a couple of months after, well, you have been discovered that you have this particular kind of illness, and based, of course, on whether you're going to be treated or not. Well, then you should realize, of course, that whatever this yi that we have over here is, that we can only observe one of these two outcomes. Either the individual received the treatment, so si is equal to 1, and then we do observe yi1, but we do not know anything, we are completely ignorant about how the health status of that particular individual would have been in the case that that particular individual would not have received the treatment. On the other hand, at the moment that si is equal to 0, so the individual did not receive a treatment, well, then we do know that what yi0 is, but we have no idea what yi1 would have been, what would have been the health status of the particular individual in the case that he would have received, or she would have received, a treatment. So therefore we should realize that this actually fits into the model that we have over here. But we should also realize that we do not only have medical examples. We can even think more in terms of economics or econometrics. We can come back to the example that we already had with respect to, say, having a college degree or not. As I equal to 1 could here be also, as we had in the previous slide, well, an indicator for whether you have a college degree or not. And then yi is going to be your hourly wage. And then we should realize that yi1 and yi0 are then simply the hourly wage that you receive at the moment that you have, say, a university degree, and at the moment that that same individual doesn't have a university degree. We should take into account that for any individual that we can think of the, say, college degree wage and the non-college degree wage, so the wage that that particular individual would have received at the moment that he or she has no college degree. Well, also here you should realize that we have exactly the same problem as what we have seen before. At the moment that we're going to look at an individual that has a college degree, well, for example, I have a college degree, we can look at the college degree wage, the wage that that particular individual receives at the moment that that particular individual has a college degree, because of the fact that that's just the wage that that particular individual receives. My wage is my college degree wage. However, you should realize that nobody actually knows, even me, I have no idea what I would have received in the case that I would have decided not to go for college. So therefore, for any individual that we have in the world that has a college degree, we do observe the college degree wage, but we do not observe this thing that we have over here. On the other hand, if we have an individual that didn't go to college, well, then we of course do observe the non-college degree wage, so this thing that we have over here, but we are ignorant about this thing that we have over there. Well, whether this is going to give us any problems or not, that's of course another question. But before we are going to think about that, it is already good to think about, well, what is actually the impact that a particular treatment is going to have on the outcome. So therefore what we're going to think about first is whether, well, what is in fact the impact of a particular treatment and how can we actually measure it? Well, we should realize that we can look at many different, say, measurements with respect to how the treatment is going to affect the outcome that we have over here. It's not immediately clear which is going to be the best, say, measurement that we can ever think about. But one thing that has been looked at many times in the literature is a so-called average treatment effect. What is the average treatment effect? Well, the average treatment effect is actually nothing else as the mean of the difference in the outcome. So it's the mean of the difference between yi1 and yi0. Well, this you can actually also say in a little bit different way. So it's not only the mean of the differences between the outcomes that we have over here, but you can also give it a little bit of an easier interpretation because of the fact that this is also equal to, well, the mean outcome that we are going to observe. If everybody in our, say, population is going to be treated, so it has an SI equal to 1, minus the mean outcome that we would have observed in the case that everybody in our population would have had an SI equal to 0. So to come back to the example that we had before with respect to college education, this average treatment effect is actually nothing else as the mean outcome that we observe in the case that everybody in our population, say for example the Dutch working population, would have had a college degree. Even the individuals that of course do not have a college degree right now, minus the mean, say, wage that we would have observed in the case that nobody in our, say, population would have had a college degree. So that's the average treatment effect. Well, as I already said, it is just one of the possible, say, measurements that we could actually look at. In some cases, this is a very nice thing to look at, but we should take into account that that's not always the case. At the moment that, for example, we are going to look at the impact of education, and we would like to know whether we have been spending a couple of billions here in the Netherlands on, say, university education, and maybe the, say, Ministry of Education would like to know a little bit more about, well, did we actually do good? Did we actually, the people that we educated, do they actually receive a higher wage? Well, then you should realize that this average treatment effect may not be such a good indicator. And the reason behind that is because of the fact that actually even looking at the impact among those individuals that have never been educated. If we would have been in a bad situation, and we have a lot of, say, soccer players that we have over here in this population, they all have a negative and a quite negative return to education. So therefore, this thing could actually be quite negative at the moment that we have a lot of people in there that have a negative return to education. But does that say that we do bad by educated individuals? Well, that is not that clear because of the fact that we haven't educated actually these soccer players. We haven't been educating these individuals with a negative return to education. So therefore, it could be much better not to look at the average treatment effect by itself, but just looking at the, say, average treatment effect among those individuals that were really educated. And that is usually related to the so-called average treatment effect among the treated. The average treatment effect among the treated only looks at the, say, impact that we have among those individuals that have an SI equal to 1. So it's here also the mean, say, impact of going from SI equal to 0 to SI equal to 1, but only among those individuals that have an SI equal to 1. So we should realize that this has a different interpretation. It's the, say, difference between, well, what we are going to observe right now among those individuals that have an SI equal to 1, minus what we would have observed among those individuals if their SI would have been equal to 0. So in terms of the wages, it's the mean difference between the wages of individuals that have a college degree minus what they would have observed in the case that they would not have had a college degree. Well, it's interesting to see what the average treatment effect and the average treatment effect among the treated would have been in the case that we would have looked at the standard linear regression model. So suppose that the standard linear regression model is the truth. So then the question arises, what is then the average treatment effect and the average treatment effect among the treated? Well, remember that then what we're going to get is this model over here. We have beta I is beta 0. I'm sorry, yi is equal to beta 0 plus beta 1 times si plus ui. And then what we're going to see is that yi1 is always equal to beta 0 plus beta 1 plus ui. And yi0 is always going to be equal to beta 0 plus ui. Well, then how we are going to compute it is not that important, but it's immediately clear that yi minus y0 is always equal to beta 1. So therefore, both the average treatment effect as well as the average treatment effect among the treated will be equal to this beta 1 that we have over here. And we do also know that if S and U are uncorrelated with each other, well then at that moment in time we can simply estimate it with respect to ordinary squares. Ordinary squares will say unbiasedly but also consistently estimate this beta 1 that we have over here. So that is really nice. However, the question of course arises, what is going to happen at the moment that we are going to be in a situation in which this S could actually be correlated with the U that we have over there? That could of course be possible. It could be possible that this S that we have over here is correlated with UI in the case that the talents that you need in order to receive higher education are going to be correlated with the talents that you actually need at, say, receiving a high wage, that you need at the labor market. It could be possible that, for example, well, how smart you are may actually be related to, well, how likely it is that you're going to have a college degree. Generally, we expect that more intelligent individuals, also the individuals that are more likely to have a college degree. However, if being smart, being a smart person, being intelligent also helps you to receive a higher weight by itself, well then at that moment in time, S and U, they are going to be correlated with each other. You can also think of other characteristics, other talents, such as, for example, communication skills. If communication skills are going to help you both at university as well as at the moment that you're going to get a job, well then these S and U, they are going to be correlated with each other. So the question arises, what to do in that particular case? Well, we already know that. We know that then we should use IV estimation. We should try to find an instrument, and then in that particular situation it would be possible to consistently estimate this beta 1 that we've over here. Well, I'm pretty sure that you already know that, how that actually works, but let's explain this once more, and let's explain this in a very simple situation in which we are going to have a binary instrument. So our instrument that I'm going to note here by Z can only take two values. It's either equal to 0 or it's equal to 1. Well, what we do then, if the case that we're going to look at IV estimation, the whole idea behind IV estimation is that we are then no longer going to look at the mean of y conditional on S. What we actually do at the moment, we're going to look at ordinary squares. Ordinary squares actually nothing else is a smart way to look at conditional means. But what we're going to do now is that we're going to now look at the mean of y conditional on Z, on this Z that we've over there. And we do assume that it's a good instrument, so therefore it's both, as we always call, both going to be an exogenous instrument as well as a relevant instrument. Well, what is this thing that we have over here? Well, based on the model that we had in the previous slide, this is of course equal to beta 0 plus beta 1 multiplied by the mean of S conditional on Z I equal to 1, whatever that is, plus the mean of U I conditional on Z I equal to 1. Well, this thing we actually know. We know what this thing is over here because by the definition of an instrument, this is an exogenous instrument, so therefore U should be uncorrelated with the outcome of Z. Therefore it's an exogenous instrument. So therefore this thing that we have over here is equal to 0. Well, in exactly the same way we can do that with respect to the mean outcome of y conditional on Z I equal to 0. That is now equal to beta 0 plus beta 1 multiplied by the mean outcome of Si conditional on Z I equal to 0 and nothing else. Well, now what we are going to see is that we actually have two restrictions and we have two unknowns, of course, beta 0 and beta 1. Well, I'm pretty sure that for you it's not that difficult to now immediately see that that means, of course, that if you're going to take the difference over here and solve for beta 1, that beta 1 is equal to the mean difference in terms of yi between the group that has a zi equal to 1 and a zi equal to 0 divided by the mean difference in terms of si conditional on z equal to 1 or z equal to 0. Luckily, this thing that we have over here, we do know that that's not equal to 0, and that's because of the fact that we have a relevant instrument. Z must have an impact on this S that we have over here, otherwise it would not have been a relevant instrument, which means that this mean, the mean of S among those individuals that have a Z equal to 1, so the mean, say, the average amount of individuals, the percentage of individuals that have a college degree, among those individuals that have a Z equal to 1 is different from the individuals that have a Z equal to 0. And this actually is our, say, famous IV estimator. Well, you should realize it's not exactly, of course, the IV estimator because of the fact that, well, this thing that we have over here, the right-hand side, is something that we cannot observe. So therefore, we typically are going to replace these, well, population means that we have over here. We're going to, well, replace them by sample means. We're simply going to look at the mean outcome in our sample of y conditional on zi equal to 1, and we do the same with all these other means that we've over here. Then we get our IV estimator for, in this case, this special case, of course, that we have a binary instrument and we have the special model that we had at the previous slide. But we do know that now our IV estimator, at the moment that we're going to estimate this thing that we've over here, is going to give us a consistent estimator. I would like now to go on with the random coefficients model. Also in the random coefficients model, we can look at the average Speedman effect, and that again is of course equal to the mean of the difference between yi1 and yi0. Well, in this case, yi1 is simply equal to beta 0 ui plus beta 1 ui, because of the fact that by definition here si is equal to 1, so therefore we get simply a 1 over there. Well, we can do the same with respect to yi0. That is now in this case just equal to beta 0 ui, because of the fact that si is now equal to 0, so we don't get anything here in addition. Well, then what we immediately see is that since this is now the mean of beta 0 ui plus beta 1 ui minus beta 0 ui, is that the beta 0 ui's, they are going to cancel to each other. So therefore we simply are going to get the mean of beta 1 ui. Well, this could have been expected because of the fact that you should realize that in the random coefficients model, beta 1 ui is in fact the direct impact of treatment going from S is 0 to S is 1. And because of the fact that this is going to be the direct treatment, beta 1 ui is going to be the direct treatment of a particular individual, what we're going to do is that we're going to simply, in the average treatment effect, take the average, the mean, over the total population. So, of course, people have different levels of ui and therefore also have a different impact here of beta 1 ui. But what we're going to do is that we're simply going to, well, take the mean of this in order to get the average treatment effect. Well, the same we can do with respect to the average treatment effect among the treated. Then again, we're going to get the mean of yi1 minus yi0, but now on the subpopulation for which si is equal to 1. So that means the subpopulation of the individuals who are treated. Well, I do think that it's immediately clear that if I do exactly the same steps as I have done over there, that then we get the mean of beta 1 ui, but now among those individuals that have an si equal to 1, so those individuals who are actually treated. So this is the mean impact, say, of beta 1 ui among those individuals who are treated. And take into account that this thing here, in the case of the random coefficients model, in the case that there is heterogeneous effects, well, then in that particular situation, unlike what we had with respect to the linear regression model, this thing is in general different from that thing that we have over there. And that's immediately clear at the moment that we're going to look at examples. Suppose, for example, that we are going to look another time at the medical treatment. So suppose that we now are going to look at a very serious disease like cancer. And at the moment that we're going to look at cancer, we do know that there is a very general treatment, and that is called chemo. But the problem with respect to chemo is, of course, that it has extremely high cost. Not so much financially, but psychologically. It's just that not that fun to have a chemo. So therefore, at the moment that you do not expect that much out of chemo, well, then at that moment in time, your SI generally will be equal to 0 because of the fact that you will, in that particular moment in time, decide not to have a chemo. So therefore, we should realize that, well, it may, of course, be possible that a medical doctor, for example, is going to tell you like, well, I don't expect that much from a chemo, so therefore it's better not to have it. That's generally, in the case of cancer, of course, a very bad situation because of the fact that that means that the medical doctor is not going to expect that you will actually recover from cancer, even with the chemo, and therefore it's better not to take it. Well, that means, of course, that we are going to expect that those individuals that are going to go for the, say, very costly chemo, well, these individuals do expect relatively a lot from that, and therefore their, say, impact of the treatment is going to be essentially better than those individuals that are deciding not to have the treatment, not to have the chemo in this case. So that means that this mean that we have over here generally is going to be different from that mean that we have over there. And we should realize that this is, of course, also true at the moment that we're going to look at the returns to education. again, at the moment that we're going to look at the impact on your hourly wage of having a college degree or not, well, then we expect that those individuals that are going to decide to go for college, well, these are generally also the individuals that expect the highest returns from college. Individuals that expect that their wage is hardly going to change at the moment that they're going to have a college degree, say the soccer players in this world. Well, these individuals, of course, are deciding not to have an SI equal to 1, so not to go for college. And the individuals that expect a very high return from college, well, these individuals, of course, are going to have a relatively high level of beta 1 UI. That means that at the moment that we're going to look at the returns to college, they will generally be higher among those individuals that decided to go for college. So this average treatment effect among the treated is generally going to be higher than the average treatment effect that we have in the total population. And therefore, generally, we can say that at the moment that people make decisions themselves about whether they're going to be treated or not, that will, of course, well, that means, of course, that at the moment that there is a random coefficients model, so if there are heterogeneous treatment effects, that then the average treatment effect among the treated is different from the average treatment effect itself. Well, but take into account that both the average treatment effect as well as the average treatment effect among the treated, they can be seen as policy relevant. They are relevant for the policy maker, and therefore the question arises, how are we able to estimate them? Well, let's first of all look at ordinary least squares. So suppose that even though we do know that the random coefficients model is the correct model, what we're going to do is that we simply are going to run an ordinary squares regression of y I on Si. Well, I do, of course, know that among econometricians, you already know for a very long period of time that what ordinary squares actually tends to do is to compare, say, different conditional means. So what we're going to do in this particular case is that at the moment that we run a regression of y I on Si, then the coefficient of Si is going to essentially try to estimate this thing that's over here. It's the mean of yi among those individuals that have an Si equal to 1 minus the mean of yi among those individuals that have an Si equal to 0. So in words, it's the mean outcome among those that are in the treatment group minus the mean outcome of those individuals that are in the control group. Well, now what we can do is that we can now simply substitute in the random coefficients model in this, in this difference that we have over here. So then we get here, we get beta 0 ui plus beta 1 ui, and there we simply get beta 0 ui. Well, now we can rewrite this a little bit, not that much actually. Here we can realize that this is a mean of a sum, so that can be, well, written as a sum of means. So therefore, we're going to get this thing over here. And here I have done one additional trick, and that is that I've taken together the impacts with respect to beta 0 ui. I've taken them together. So therefore, in total, what we're going to get is the mean of beta 0 ui among those individuals that have an Si equal to 1, minus the mean of beta 0 ui among those individuals that have an Si equal to 0, plus the mean of beta 1 ui among those individuals that have an Si equal to 1. Take into account that at the moment that we're going to do an ordinary squares regression, we're not going to get all these components over here. We simply get one outcome with respect to this thing that's over here. We don't get this thing itself, of course, we just get an estimate of this thing that we have over here. But the question, of course, arises, how does this relate with either the average treatment effect or the average treatment effect among the treated? Well, the answer to that is, well, if we're going to look at the average treatment effect among the treated, well, at least this last term that is over here is exactly equal to that term that is over there. So therefore, the answer to the question, might it be related, is that at least if these two terms are equal to 0 together, so if they add up to 0, well then ordinary squares at least is going to estimate the average treatment effect among the treated. But then the question arises, when are these two terms equal to 0? Well, there are, of course, other special cases, but you should realize that these two terms together are only generally equal to 0 in the case that U and S, they are independent from each other. Take into account that in this case, independence is necessary because of the fact that we here have functions of ui, not ui itself. And this function could be nonlinear. And therefore we need here in general that u and s, they must be independent from each other, which is of course stronger than what we had with respect to the linear regression model at the moment that we had endogenous regressors. So if u and s, at the moment that they are independent from each other, well, then we should realize that then these two things are equal to 0. And then of course ordinary squares is going to estimate for us this thing that we have over here, which is the average treatment effect among the treated. But take into account that in that particular situation, we're also going to estimate the average treatment effect, because that's a special case in which we can also delete this as I equal to 1 over here, which means, of course, that the average treatment effect and the average treatment effect among the treated, again, they are going to be exactly equal to each other. But the question, of course, arises, is that a good assumption to make? Is it good to assume that u and s, they are independent from each other? Well, the answer to that, generally not, of course. And the reason behind that is exactly for the reason that I just described. And that is that at the moment that S is based on a choice of the individual, that individuals will generally, of course, choose to have a SI equal to 1 in the case that the realization of, say, U is in such a way that beta 1 UI is going to be, say, favorable for them. But that means by definition that SI and U, they must be, well, at least be dependent upon each other. It's very unlikely then that they're completely independent from each other. So therefore, the answer to whether U and S, whether they are going to be independent from each other, we can say like, well, that will only be the case if we do not allow individuals to make decisions. So if we allow ourselves to choose with respect to S, and we're going to do that completely independent from you, well, then we can expect that you may be independent from S. But as soon as we allow individuals to make a choice with respect to S, well, then we can generally expect that U and S, they are going to be dependent upon each other. So only in the case that we decide about S, and we do that completely independent from you, which is generally called a random control trial, well, then we can expect that we are able to use ordinary squares in order to estimate the average treatment effect as well as the average treatment effect among the treated. So this is also the reason why, for example, in medical sciences, well, the only way in which we are allowed to do research is by random control trials. Well, in economics, we cannot always do that. Even though also in economics or in econometrics, we sometimes do random control trials, there are many reasons why we cannot always do that. Not going to go here into details, but we should realize that we cannot always do this thing that we have over here. So therefore, we should do something else. And the something else that we can do is, of course, to go for instrumental variable estimation. Well, in order to say whether instrumental variable estimation here is going to help us, what I need to do is that I have to introduce a little bit of notation. What we're going to have now over here is that I'm going to introduce SI. Well, we already had, of course, SI. Either SI was equal to 1 in the case of treatment, or SI was equal to 0 in the case of non-treatment. But now we're going to introduce again an instrument, and again it's going to be a binary instrument equal to 0, 1. And well, SI is equal to SI1 in the case that ZI is equal to 1, and SI is equal to SI0 in the case that ZI is equal to 0. Well, now you should realize that SI can only take outcomes equal to 0 and 1 by definition. So that means that these two things, they can also only take outcomes equal to 0 and 1. Well, now in a Nobel Prize winning article by Angrist and Imbens in 1994, I'm pretty sure that you have heard about this before. In the last Nobel Prize for economics, 2 or actually 3 econometricians won that. There was first of all David Card, but apart from that, well, half of the prize was won by these two persons that we have over here, Jos Angrist and Guido Immens. I will say this because of the fact that, well, this is especially relevant for the Netherlands because of the fact that Guido Immens, you might know, is originally from the Netherlands. Well, they won a Nobel Prize essentially for, well, not just for this article, but this article was very important with respect to that. And what they do is based on this SI that we have over here, this definition that we have over here, they're going to define, or they did define in 1994, the following groups. This is probably not the reason why they actually won the Nobel Prize. We will see that later on why they did won the Nobel Prize for this article that over here. But they define 4 different groups based on the potential outcomes that we have with respect to SI1 and SI0. First of all, we have the compliers. Compliers are simply individuals that have an SI equal to SI1 equal to 1 and an SI0 equal to 0. So these are individuals that are belonging to the treatment group if their instrument Zi is equal to 1, and they belong to the control group in the case that their instrument is equal to 0. Well, then apart from that, we also have the always takers. Always takers are individuals that have an instrument value, or I'm sorry, a treatment that is always equal to 1. So, well, unlike what we had with respect to the compliers, they always are treated. So they are treated at the moment that their instrument value is equal to 1, but they're also treated at the moment that their instrument value is equal to 0. Well, apart from the always takers, we also have the never takers, and never takers are actually individuals that are never treated. So that is independent on whether their, say, instrument outcome is equal to 1 or 0. So there we have that at the moment that their, say, instrument outcome is equal to 1, then they have a 0, but it's also equal to 0 in the case that their instrument outcome is equal to 0. And then finally, we have the so-called defiers. And defiers are individuals that are actually completely opposite from the compliers. They are going to be, say, treated at the moment that their instrument outcome is equal to 0, and they're not going to be treated at the moment that their instrument outcome is equal to 1. Well, in order to understand this a little bit better, it's not necessary to immediately think, of course, of a particular instrument, but one thing that you could actually think about is that Zi could be the intention to treat. Even in the case that you're going to run a random control trial, you should realize that it's not always, that you do not always have the full control of who is going to be treated or not. You can try to have somebody treated in medical treatment, but in general, suppose, for example, that somebody has to take a pill or something like that, the patient can always decide not to take the pill in the end, so not to take the treatment in the end. Well, suppose that both are observed, so you know the outcome of the random control trial, and you also know whether somebody's treated or not, so this SI that is over here. Take into account that SI could be endogenous in this case, because of the fact that people that don't expect too much from the treatment, even in the case that they are intended to treat, so they are in the treatment group according to the random control trial, they are going to decide not to take the treatment. So these are individuals that generally expect not too much from the treatment. Well, take into account that therefore this thing that over here is endogenous, but this thing over here, given the fact that it's from a random control trial, is completely, say, exogenous. It's not correlated with anything. Well, it could essentially in random control trials also be the other way around. It could be the possibility that we have that somebody is not going to be in the random control trial, but it could be possible that a medical doctor decides to still treat that particular patient if the case that in the case that he or she expects a really high return to the treatment. So therefore we can see that SI here, the treatment itself, could be different from the intention to treat. But it's not really necessary. It could also be the case that we could actually look at, again, the returns to education. Also in the returns to education, we could think of a situation in which we are going to have a Zi, a binary Zi that we have over here. For example, in the Netherlands, we could look at a very interesting example that's relevant for you. And that is that in the Netherlands for a long time, it used to be the case that individuals received a so-called scholarship. You could receive a scholarship. Well, you didn't actually have to really do something for that. Everybody was receiving a scholarship for a long period of time. In the 70s, it was quite high. It was reduced in the 80s and 90s. And then, well, in 2013, well, the government decided not to have that scholarship any longer. Well, that's of course important for whether you're going to go for university or not. At the moment that you decide to go for university, then you will actually take into account whether you're going to receive a scholarship or not. So therefore, one thing that we could do in this case is compare, of course, individuals that are born in different years. Suppose that you're, for example, born 18 years before 2014. Well, then in that particular situation, at the moment that you had to decide about going to university or not, well, you knew that the likelihood that you're going to receive ever a scholarship was actually quite low. So therefore, it may be possible that you decide not to go for university, or at least the likelihood will be lower. As for example, an individual that is born in, well, 18 years before 2010, individuals that had to decide at their 18th birthday whether they're going to go for college or not. In the year 2010, well, they had the idea that they were going to still receive a scholarship for the whole period that they were going to study. So therefore, these individuals may be more likely to go for university than individuals that decided not that actually were born in 18 years before 2014. And therefore, this may actually have an impact. But take into account that in this case, Zi, the year in which you are born, is not really related to, say, generally what you're going to receive at the moment that you go for college or not. So therefore, it's not really related to the outcome itself, but it does have an impact on whether you're going to go for college or not. But whatever it is, what we can do is that we can make the following assumptions. We can assume that U and Si1 and Si0, they're going to be independent from Zi. Based on this assumption, which is again, of course, a much stronger assumption that we know from well, the standard linear regression model, which just assumes that Zi should be well, independent from this Ui that we have over here. Take into account, by the way, that this assumption that we have over here doesn't mean that Zi is an irrelevant instrument. You might think that that's the case because of the fact that well, we have here Si1 and Si0, which should be independent from Zi. But what you should realize is that in this particular case, we are just going to assume that at the moment that you're going to have Zi equal to 1, then at that moment in time, well, the likelihood that you're going to participate, well, that you're going to be treated is actually not directly affected by Zi itself, of course, but the outcome, of course, is affected by Zi by the fact that at the moment that you do have a Zi equal to 1, then you're going to receive an Si1 rather than an Si0. But what we here are assuming that even though, of course, individuals that have different levels of Zi, they have different, say, outcomes with respect to whether they're treated or not, the likelihood of whether they're going to be treated should not be dependent, in fact, on this Zi, given, in fact, that we already know that Zi is equal to 0, 1. So that's the assumption that we're going to make over here. Well, based on this assumption, what we can do is that we can now ask ourselves the question, well, what does the IV estimator try to estimate in this case? Well, we do already know something about the IV estimator. We do know that the IV estimator has a numerator divided by the denominator. So therefore, the first thing we can do is that we can look now at the numerator. That is, we already know this thing that we have over here. The mean of yi conditional on Zi equal to 1 minus the mean of yi conditional on Zi equal to 0. Well, then what we can do is that we can now substitute in the, say, random coefficients model. So here we get beta 0 ui plus beta 1 ui times Si, and here we get exactly the same. Unfortunately, in this case, we cannot just say like, well, Si is equal to 0, 1 because of the fact that now we condition on the Zi and no longer on Si. However, based on what we had in the previous slide, we can just still say that this is equal to Si1, and this is of course equal to Si0. So therefore we can write it in this way that we've over here. And now we can realize that we have this assumption that we've over here, which means of course that both Ui as well as Si1, they're independent from Zi. So therefore we do not have to condition here on Zi equal to 1. So therefore I can simply delete this Zi equal to 1 that we've over here. Exactly the same holds true at the moment that we're going to look over here. Beta 1 Ui as well as Si0, they are independent from this Zi equal to 0 equal that we have over here. So therefore we can also just delete this thing that we have over here. So therefore I can also write it like this. Well, then you should realize that I can make this much simpler. I can just take these two means together in order to get now this relatively nice thing that we have over here. But I'm going to make it a little bit more ugly, this relationship that we have over here. And the reason behind that is because of the fact that I should realize that Si1 minus Si0 can actually only have 3 different outcomes. Either we are going to have that Si1 minus Si0, well, what we can have is that Si1 is equal to 1 and Si0 is equal to 0. Then, of course, this difference that we have over here is simply equal to 1. That is in the case that we, of course, have a complier based on the definitions that we had in the previous slide. Well, it could also be possible that Si1 minus Si0 is simply equal to 0. There are 2 situations in which this is going to be true because of the fact that either Si1 and Si0, they're equal to 1, or they're both equal to 0. In both cases, we are going to have that this difference that we have over here is equal to 0. So that's in the case of either the always takers or the never takers. However, it is still also possible that Si1 is equal to 0, and this thing that we have over here is equal to 1. Then we get an outcome equal to minus 1. That's the case of the so-called defiers. And then you should realize that, well, then this outcome that we have over here is equal to minus 1. So that implies essentially that we only have 2 relevant outcomes for this mean that we have over here, because of the fact that Si1 minus Si0 case is equal to 0 is not relevant, because then we simply get a 0 over here. We have only 2 relevant cases. Either Si1 minus Si0 is equal to 1 in the case of the compliers, or this difference is equal to minus 1 in the case of the, say, defiers. So then, based on the law of iterated expectation, what we can do is that we can simply write here beta 1 Ui multiplied, of course, by 1, conditional on the fact that this difference is equal to 1, multiplied by the probability that this thing is equal to 1, plus, of course, well, the mean or the conditional mean of minus beta 1 Ui. So maybe better to say minus the mean of beta 1 Ui, well, multiplied, of course, by minus 1, but that gives us a minus sign in front. Conditional, of course, on the fact that this is equal to minus 1, multiplied by its probability. So therefore, in total, what we're going to get is this whole thing that we have over here. This is the mean, say, impact that we're going to have among the so-called compliers, multiplied by the fact that we are going to have a complier, minus the mean impact that we have among the defiers, that's this thing over here, multiplied by the probability that we do have a defier. Well, we can also look at the denominator. We can use more or less the same steps for the denominator. Remember that the denominator is actually nothing else as this difference that we have over here. Then we can write this as Si1 and this as Si0 in order to get this difference now that we have over here. Well, then again, we can realize that Si1 and Si0, they're independent from Zi, so therefore we can get rid of this part over here as well as this part over here to simply write like this. But now I should realize that this actually can only take, again, 2 relevant outcomes. Either this thing is equal to 1, in the case that Si1 minus Si0 is equal to 1, of course. So that has a probability equal to the probability that SI1 minus SI0 is equal to 1, minus, of course, the probability that SI1 minus SI0 is equal to -1. So therefore, we can even write it like this thing over here. So therefore, the question, what does IV estimate? Well, that's of course nothing else as the numerator divided by this denominator that is over here. So in total, what we're going to get is this, say, ugly representation that we have over here. This is, first of all, ugly, of course, because of the fact that we have here a really long numerator, but take into account it's exactly equal to that thing that we have over there. But the most important thing, why it is actually ugly, is because of the fact that it's completely meaningless. What is this thing that we have here over here? Well, I can't give it any interpretation because of the fact that, as I already said, interpretation that it actually has, at least the numerator, is, well, it's the mean impact among the compliers multiplied by the percentage of compliers that I do have in my population, minus the mean impact that I have among the defiers multiplied by the probability that we have of defiers, so the, say, percentage of defiers that we have in our population. I have no idea what it is. I even have no idea what actually the sign of this thing is if we have, say, for example, a positive impact, because we even have here a minus sign in front of, say, the impact that we have over here. So at the moment that the defiers have a large positive impact, then this thing actually over here is going to be positive, even though, well, among the defiers, I'm sorry, it's of course going to be negative, but among the defiers, it was actually positive. So therefore, what we should see over here is that this relationship that we have over here, well, doesn't make any sense. And it doesn't become any better by, well, looking at the denominator, defining it by the denominator. So the answer to the question, does IV estimate anything meaningful? Well, the answer to that, not at least in this case. In this case, we can actually say that doing an IV regression doesn't give us anything which is going to be meaningful for us. However, what we can do is that we can make an additional assumption. Let's assume that we do not have any defiers in our population. So that means nothing else, that we simply are going to assume that the probability of having a defier in our population simply is equal to 0. What does that mean? Well, that means something with respect to the context that we have. Whether it's a restrictive assumption or not, really depends on the context that we are looking at. Suppose, for example, that again, Zi is the intention to treat. Well, then essentially being a defier means nothing else is that at the moment that you are intended to treat, so you belong to the, say, treatment group from the RCT, from the random control trial, well, then you're going to be not treated at the moment that you're intended to treat, according to this rule that we have over here. And at the moment that you do not belong to the treatment group, according to the RCT, well, then in that moment in time, you're actually going to be treated. Well, that in the case of a medical experiment doesn't make that much of sense. Why should actually somebody decide to, well, say, treat him or herself at the moment that you actually have the opportunity to treat yourself, and not do that at the moment that you do not have that particular opportunity? So therefore, at the moment that Zi is, for example, the intention to treat, well, the likelihood of having a defier is, of course, equal to 0. But we should also take into account that that is also the case at the moment that we're going to look at this example that over here. At the moment that we're going to compare different individuals with each other, whether they have a scholarship or not, then it's going to be very unlikely that somebody is going to decide to go for college at the moment that that particular individual doesn't have a, say, scholarship, whereas somebody is going to decide not to go for scholarship at the moment that, I'm sorry, not to go for college at the moment that you do have a scholarship. So therefore, we could also say in this particular case that having a defier in our population is very unlikely to be the case. So therefore, in general, what we can say is that, well, in particular examples, and especially in the examples that are over here, it might not be so restrictive to just say like, well, defiers do not exist in our population. But then you should realize that the equation that we have over here, well, that becomes much simpler. And the reason behind that is because of the fact that we should realize that then, first of all, this thing, of course, is going to drop out. Also, this thing is going to drop out, but take also into account that these two things, they're also going to say cancel to each other. So that means that in that particular case, IV estimation means nothing else is that we are trying to estimate this object over here. And what is this object? Well, this is simply nothing else as the mean impact that we expect among, say, the compliers. And this, of course, does have, say, an interpretation. It just says that, well, what we're going to do is that we are going to have a subset of individuals who we can call compliers. These are individuals, of course, that are going to be, well, not treated at the moment that their z is equal to 0. They're going to be treated at the moment that their z is equal to 1, which means nothing else is that the instrument, the change of the instrument, makes them actually change their state of treatment. Well, and then what we're going to do is that we're going to look at that subset, and we're going to look at what their impact is with respect to the treatment. Well, this, say, object that we have over here, Angrist and Immons call that the so-called local average treatment effect. Well, they usually call this late. And this is probably the main reason why they actually received the Nobel Prize, because they were the first actually to look at late, and late has been later on the general idea behind IV estimation. But based on this whole thing that we now have described, we should realize that we can now get two conclusions from this. Well, first of all, we should realize that IV needs additional assumptions in the case that there is impact heterogeneity. So in the case that we can expect that the treatment is going to be, well, having an heterogeneous impact, well, then we need additional assumptions from the standard assumptions with respect to IV estimation. First of all, then we need independence, as we have seen, not just the U and S have to be uncorrelated with each other, but they even have to be, well, independent from each other, or at least the instrument has to be independent. And in addition to that, we also have here that we need this assumption that we have over here, that there are actually no defiers. That's usually called the monotonicity assumption. So these are two additional assumptions that we need for instrumental variable estimation. But maybe more important is that you should realize that late, or in fact what we estimate here with respect to IV, is actually an object that depends on the chosen instrument. So apart, of course, that it depends on how this beta 1 UI looks like, it also depends on the chosen instrument. And the reason behind that is because of the fact that our compliers, the group of compliers, depends on the chosen instrument. As soon as I'm going to choose another instrument, then my group of compliers is also going to be different. And that is going to have an impact on this late estimator that we have over here. And that brings with it something which is not that nice. And that means, in fact, nothing else is that suppose that we have two researchers that try to look at exactly the same thing. They might use the same model. It may even be possible that they use exactly the same data set. However, suppose that the first researcher is going to use another instrument than the second researcher. Well, what you should realize with respect to late is that if we're going to use instrumental variable estimation, then it may be possible that, say, the late estimator that the first researcher is going to receive may be different from the second researcher. And that actually implies that it may even be the case that even the, say, sign with respect to late may actually switch with respect to the instrument. It may be the case even, this is of course quite extreme, but it may even be the case that the first researcher is going to say like, well, based on my instrument, I actually have a negative impact with respect to late, whereas the other one is going to say like, well, I actually have a positive impact. And both are going to do well, they essentially do correct research. It's not that one of the two actually makes the wrong assumptions or uses the wrong model or the wrong data set. It's just that they use different instruments and therefore come to different conclusions. Well, this has all to do, in fact, with the fact that you realize that late, unlike the average treatment effect, as well as the average treatment effect among the treated, it's not policy relevant. This is not something that is relevant for the policymaker. The policymaker doesn't want to know, of course, what the mean impact is among, say, the individuals who are compliers. The policymaker is even not interested in compliance. The policymaker is probably interested in what is the impact generally for any individual that we have in our population, and especially among the individuals that, of course, are treated. But it's not interested essentially in this thing that we have over here. So therefore, because of the fact that late is not policy relevant, it may be better to look at other things. Well, Heckman and Whitlassil, in an Econometrica article in 2005, tried to say look at policy relevant instrument, policy relevant objects, such as, for example, the say average treatment effect, as well as the average treatment effect among the treated, based on instrumental variable estimation. So it asks the question, suppose that we still want to do instrumental variable estimation, how can we actually, well, try to estimate things that are policy relevant rather than this late that we have over here? Well, now another interesting topic is whether we should always look at averages. We should realize that the average treatment effect, as well as the average treatment effect among the treated, they're completely based on averages, on means. And the question arises whether it's always interesting to look at means, or whether it's also good to look at other things, such as, for example, quantiles. Let's look at a very simple example. Suppose that we have a particular policy, and suppose that the policy has, on average, a very mild positive effect among the whole, say, population that we have. So to speak, in terms of the average treatment effect, the average treatment effect is mildly positive. But at the same time, we're going to see that the policy, whatever it is, has a very negative impact among the individuals that are really at the bottom of the, for example, income distribution. Well, you should realize that a lot of policymakers may be interested in that. They may actually change their decision at the moment that they know that some individuals are really heavily, say, negatively affected by a particular policy. Well, average treatment effects don't look at that. So therefore, we should also look at other things, such as, for example, quantile treatment effects. I'd like to go on with the next topic, and that is the topic of invariance to monotonic transformations. What we should realize is that at the moment that we're going to compare quantiles, and especially at the moment that we're going to look at quantile regressions, we're going to see many times that quantile regression is much more difficult than looking at standard regression. In general, quantiles, they are relatively difficult. However, there are things that are difficult at the moment that we're going to look at standard regression, or at least things which are not possible at the moment that we're going to look at standard regression, which we will later on see are going to be relatively straightforward at the moment that we're going to look at quantiles and quantile regression. And that is usually related to the topic that I'm going to discuss right now. And that is that quantiles are so-called invariant to monotonic transformations. In order to introduce that, suppose that we have g, and suppose that g is a monotonic function. Here we say an increasing function, but it's also not a problem at the moment that g is a decreasing function, but it has to be monotonic, either increasing or decreasing. And then what we're going to do is we're going to introduce the following stochastic variable. Z is a function of another random variable y, where the relationship is that z is simply equal to g evaluated in y. Well, it is immediately clear that z, of course, is random because of the fact that y is random. But we would like to relate the quantiles of the random variable z with respect to the random, well, the quantiles of the random variable y. How are we going to do that? Well, the first thing that we can do is that we can, of course, simply look at the definition of a quantile. We do know that a quantile is always that number that is going to make, in this case, the probability that z is smaller or equal to that number equal to tau. And here, for, well, reasons that become clear later on, I'm going to denote the quantile of z simply by the quantile of gy. Well, that's of course the same because of the fact that z is equal to gy. Well, at the moment that we're going to look at this thing over here, we should immediately realize that what we can do is that we can, of course, substitute in here that z is equal to gy. So therefore I can also write it in this way that we have over here. And then what I can do next is that I can take the inverse here from the left and the right hand side with respect to this function g that we have over here. And that is allowed because of the fact that we do know that g is an increasing function. So therefore we can take the, well, inverse from this function and that function that we have over there at the left and the right hand side, and that means that now we are going to have the probability that y is smaller or equal to this inverse, which is equal to tau. That actually implies that this is no longer the definition of a, say, quantile of z, but now we actually have the definition of the quantile of y, because of the fact that the quantile of y is always equal to that number that makes the probability y is smaller than a number equal to tau, and it's exactly this number that we have over here. So that implies that this thing that we have over here must be by definition the quantile of y, and that's what I've written down over here. The quantile of y must therefore be equal to, well, the inverse function of g evaluated in our quantile. Well, but then what we can do is that we can then, well, take another time from the left and the right hand side an inverse of this inverse function that we have over here. That's of course the function g itself. So therefore, if we're going to do that, well, then the inverses, of course, they're going to cancel each other, and here we simply get our function g evaluated in our quantile, which actually says nothing else that the function of a quantile is the quantile of a function. And that's important because of the fact that now what we can do is that we can relate the quantile of z, which we have here at the right hand side, to the quantile of y, because of the fact that the only thing we need to do is to evaluate the function g in the quantiles of y. So let's look at a very simple example. Suppose that gy is equal to the logarithm of y. Well, this is of course an increasing function, and that implies of course that in this particular case, if we would like to look at the quantile of, say, log y, that's actually nothing else as the logarithm of the quantiles of y. Suppose, for example, again, that we are going to look at, for example, monthly wages, and suppose that we do know that the median monthly wage is equal to 5,000 euros. Then the question arises, can we say, based on that, anything on, say, the median log wage? The median log monthly wage? Well, the answer to that is that, well, even without being able to calculate it, we can just take the logarithm of 5,000, and then we do have the median of the log monthly wage. This sounds quite straightforward, but take into account that this is, for example, not the case at the moment that we're going to look at the mean. We do already know that at the moment that we're going to look at the mean of a function, that's generally not equal to the function evaluating the mean. This is only true at the moment that either y is deterministic, so then in that particular situation we don't really have a random variable with respect to y, or at the moment that g is linear. But in general, for example, at the moment that we're going to look at this logarithmic function that we have over here, we cannot simply say that the mean of a function is the function evaluating mean. Okay, I would like to go on with the next topic, and that's the topic of the asymptotic distribution of the quantile estimator. What we have so far is that we already have a quantile estimator, and we do know that that quantile estimator is consistent, but we haven't said anything yet about the asymptotic distribution of the quantile estimator. And that's what we would like to do right now. For that, we are going to write our quantile estimator a little bit different. Remember that the quantile estimator was actually nothing else as the, say, minimum of a particular function, a particular criterion function. In that sense, it would be best to actually go back there, because of the fact that we already know that it was actually the minimum of this function that we have over here. Well, in order to find that minimum, we already know what to do. What we need to do is to take the first order derivative and set that equal to 0. And that is actually what we have written down in the slide that I just had. So going back to that particular slide, here we have that the quantile estimator, our Q hat, is that value that is going to solve our first order condition. Well, take into account that I have already rewritten this a little bit because of the fact that I have multiplied the left and right hand side by the square root of n. For the right hand side that makes no difference, but for the left hand side we're going to have now 1 over the square root of n, rather than, say, this thing that we have over here. So therefore we can now look at a so-called Taylor series expansion. I'm going to use a Taylor series expansion over here around the truth value of this Q, the quantile that we have, and I'm just going to write that as Q tau y1 itself. I'm not going to use here 0 or something like that. This is already the true value that we actually are looking at. That means, of course, that at the moment that we're going to look at the Taylor series expansion, that the first term in the Taylor series expansion is just exactly equal to what we have over here, but instead of having Q equal to Q hat, we have Q equal to the, say, quantile itself. Then the second term that we're going to have in our Taylor series expansion is always going to be the first order derivative of this term that we have here at the left hand side, but that is already a first order derivative, so therefore we're going to get a second order derivative. Here we have a second order derivative, and of course we're not going to evaluate it again in Q hat, but we're going to do it in Q itself. So therefore we're going to get this thing that we have over here, and then we multiply that always by the difference where we're going to evaluate our function, that's of course in Q hat, minus where we can approximate our function, and take into account that our Taylor series expansion here is around Q, so therefore we get here the Q itself. So therefore we get the difference from Q hat minus Q. And then our final term is always going to be our remaining term, the rest term, that we usually call the order term. And this is going to be a little bit different from our standard calculus classes, because of the fact that we should realize in this case that what we have over here are stochastic terms. This term is stochastic, and that term that we have over there is stochastic as well, because of the fact that we have yi in there. So therefore what we have to do is that we have to look here not at standard order terms, but we're going to look at the stochastic order terms. So therefore what we're going to get is here, instead of O1, we are going to get here an OP1. And OP1 means nothing else is that we are going to have some kind of random sequence. We don't exactly know what it is, but that random sequence is going to converge towards 0 at the moment that n goes to infinity. It converges towards 0 in probability. Well, and then we need to multiply this OP1 term by the highest term that we have in our Taylor series expansion. That's of course this term that we have over here. So therefore we are going to have then, well, the difference of Q hat minus Q over here. So this is the highest order term that we already had over there. And then we can use a trick. What we can use here is that we do of course know that by definition this thing that we have here at the left hand side is equal to what we have here at the left hand side. And the reason behind that is of course this order term. This order term makes the, well, these two things exactly equal to each other. Of course the first two terms, they are of course just like an approximation, but the last term makes the, say, approximation equal to what we have over there. And then we should realize that this thing that over here is equal to 0, so that means of course as well that, well, these three terms that we have over here must be equal to 0. Well, and then what I'm going to do next is that I'm going to now multiply this term that we have over here, the second term that we have over here, by the square root of n divided by the square root of n. The reason why I'm going to do that is because of the fact that first of all, then this is going to be equal to 1 over n. Here we have square root of n multiplied by square root of n. So we get here 1 over n. And I'm going to bring this square root of n, I'm going to bring it there. And that's an important step. And the reason behind that is because of the fact that we should realize that we are interested in the asymptotic distribution of the quantile estimator. That doesn't mean, of course, that what we are going to look at is the, say, asymptotic distribution of this q hat that we have over here. The reason behind that is because of the fact that the asymptotic distribution of q hat, well, what is the distribution of q hat if n goes to infinity? Well, q hat actually doesn't go to any distribution. It doesn't converge in distribution, but it actually converges in probability. It converges to, well, actually this thing that we have over here in, say, in probability. So therefore, well, we are not that much interested in, say, the distribution or the asymptotic distribution of this thing over here. But what we typically do is that we're going to look at the difference between our estimator with what we want to estimate, in this case q hat minus q, multiplied by the square root of n. And now we do, of course, know that this difference that we have over here, it's going to converge towards 0 in probability. But at the moment that we're going to multiply that by the square root of n, we do know that the square root of n is going to converge, well, actually not in probability, but deterministically towards infinity if n goes to infinity. And that means, of course, that it's quite challenging to know what the, say, what this term is going to converge to. But that's the thing that we're going to do. Well, that means that what we want to have is this term here at the left-hand side and everything else at the right-hand side. So the first thing I can do is that I can bring this term that we have over here to the right-hand side, and the same I can actually do with respect to this term that we have over here. Then we, of course, get a minus sign in front of this term over here. With respect to OP1, I'm not going to do anything. And the reason behind that is because of the fact that plus or minus OP1, that is really no difference. And then what I can do is that I can divide now the left and the right hand side by this term that we have over here. If I'm going to do that, then in the end what I'm going to get is, well, the square root of n multiplied by q hat minus q at the left hand side. That's exactly what I wanted. And then at the right hand side I get, first of all, this term that we have over here plus the OP1 term that we have over there. And now we should realize that this is exactly what I wanted, because of the fact that now I have the left hand side. I actually have what I want to get my asymptotic distribution of. And on the right hand side I have a couple of terms. And if I can prove that the right hand side is going to, say, converge in distribution to something, well, so of course it's going to be the left hand side. So that is what we would like to do right now. Well, then the first thing we can do is that we can look at this OP1 term. However, this OP1 term is going to converge in probability towards 0, and quite quickly. And the reason behind that, first of all, that by the definition of OP1, this is going to converge towards 0 in probability. But this thing that we have over here is also going to converge in probability towards 0. And the reason behind that is because of the fact that this is going to converge to that thing that we have over there. So therefore, this whole thing is going to converge very quickly in probability towards 0. So I don't have to take that anymore into account. But what about this term that we have over here? This is a very difficult term because it has a numerator and a denominator. So therefore, the best thing to do first is to actually just focus here on the numerators. We will see is the most difficult part in the end. What is this thing over here? Well, we can first of all rewrite it a little bit by, again, multiplying this by the square root of n divided by the square root of n. I can another time take these square root of n's, I can take them together. We can take it, we get another time 1 over n, and then we still have this square root of n over here. Question, of course, arises, what is this going to converge to? Well, the first thing that you should realize over here is that this is a sample mean. It's always the case that if we are going to sum over, say, all of our observations, and we divide by n, that's a sample mean. We do know from the law of large numbers that a sample mean is going to converge to its corresponding population mean. However, the problem that we have over here is that we still are going to multiply this by the square root of n, and since the square root of n is going to converge towards infinity, Well, that doesn't work, right? So we have to do here something. Well, what we can do now is that we can use another important theorem, and that's the central limit theorem. The central limit theorem says that under certain conditions, a sample mean multiplied by the square root of n is going to converge to a normal distribution with a mean equal to the corresponding population mean and a variance equal to the corresponding population variance. So that is now what we can do. Let's first of all look at the population mean. What is that? Well, generally speaking, or maybe very sloppily speaking, going from a, say, sample mean to a population means that we are going to get rid of the summation. We are not going to have any summation, but we are going to look at the expectation. We're not going to sum over all the observation, but just the first observation, and we get rid of the 1 over n over here. In order to get this thing that we have here at the left hand side, I still have the minus sign in front because of the fact that we had a minus sign over there. The question arises, what is this thing that we have here at the left hand side? Well, we actually know this thing over here. And the reason behind that is because of the fact that we should realize that what Q actually is that we have at a certain moment in time shown that Q actually, the quantile, is actually nothing else as the minimum of a particular criterion function. For that we have to go a little bit back. It was actually over here. Here we see that the quantile is always the minimum of this function that we have over here. So therefore, in order to get this quantile, what we need to do is to take the first order derivative. And what we actually had on our slide was the left-hand side of that particular first order derivative. The right-hand side is of course always equal to 0. So that means of course as well that our, say, mean that we had, the mean of the first order derivative, is equal to 0. So this thing that we have over here must be equal to 0. What about the variance? Well, the variance is always equal to the second moment minus the first moment squared, but we now know that the first moment, that's this thing actually that we have over here, is equal to 0. So therefore what we need to do is that we only have to look at the second moment. Well, the second moment is actually nothing else as this mean that we have over here, but within the parentheses we don't get just the second order derivative, but we get the second order derivative squared. What is this thing that we have over here? Well, this thing is pretty difficult because it's a first order derivative evaluating Q equal to the, say, quantile. Then we are going to take the square of that, and then we have to take the mean of that particular thing that we have over there. Well, let's first of all look at the thing that we have here within the parentheses. So just look at the first order derivative of that m function that we have over there. We do already know what m function is because that's simply that thing over here. So what we need to do first is to take the first order derivative of this thing over here with respect to Q. That looks quite difficult, especially because of the fact that we have here our absolute values. But we should take into account that, well, since we are multiplying here by this indicator function, at least for taking derivatives, we should realize that this is only different from 0 at the moment that y is larger or equal to Q. So that means that this thing over here is always going to be positive. So we can also write this simply as y minus q. The opposite we see actually over here. Here, y is always smaller than q. So that means that we can write this y minus q. Well, it's negative. So we can also write it as q minus y for the first order derivative. So we can now take the first order derivative of this thing over here. Well, now there is still a little bit of a difficulty. And that is this indicator function that we have over here. What is the first order derivative of an indicator function? Well, what I will actually do here is that I will assume this thing to be constant with respect to q. That's not completely true, of course, because of the fact that we do know that this is actually a jump function. At the moment that y and q are equal to each other, then of course we have a problem because there it's even not differentiable. But what I'm going to do, since I'm not really a mathematician, what I'm going to do simply is that I'm going to assume this to be constant. So that means that we have a constant multiplied by another constant, and the only thing we need to do is to take the first order derivative of y minus q with respect to q, and that's of course equal to minus 1. So therefore we simply get here, say, minus tau multiplied by that thing that we have over there. Here we actually get nothing else as the first order derivative of q minus y with respect to q, that's of course equal to 1, and then multiplied by these two things that we have over there. So in the end, we only have these two things. Now what I need to do next is that I can take the square of this thing that we've over here. Well, for that, we should realize, of course, that minus tau squared is simply equal to tau squared. What about this thing over here? Well, we can also square it, but we should realize that an indicator function squared is just indicator function itself. And the reason behind that is because of the fact this can only take values equal to 0 and 1. And 0 and 1 are the only values in mathematics. At the moment that you square them, they stay the same. So therefore I can simply write this another time as the indicator function. So we get here tau squared multiplied by the indicator function. Here we get 1 minus tau squared multiplied by the indicator function, exactly as what we have over here. Now you might of course say like, well, you're forgetting about something, because if we have two terms and we square them, well then apart from squaring the terms itself, we also need the, say, cross term. We have to get 2 times this thing multiplied by that thing. But we should realize that that's always equal to 0. And the reason behind that is because of the fact that suppose that this indicator function over here is equal to 1. That means of course that y is larger than q. But then by definition, this thing must be equal to 0 because of the fact that then y is actually not smaller or equal to q if it's already larger than q. And that means of course that if we multiply these two things with each other, I always get a 0. So therefore I don't have to take that into account, and we're actually done by looking at this term that is over here. But then finally we should realize that what I want is of course not the, say, this thing squared by itself, but I would like to take the mean over it. So therefore we're going to look at the mean, and the mean of course is nothing else as an integral with respect to another time the full support with respect to y. Then we are going to get exactly that term that is over there, but now the running variable of course is this little y div over here multiplied by the density of y1 as we have it over here. Well, then the next thing that I can do is that I can simply substitute this into there in order now to receive this thing over here, where I did replace of course the q by the quantile. So therefore here I get a quantile and I get a quantile over there. Well, now I can take a couple of steps that we already have done before. The first thing that I can do is to bring the density function now into the parentheses. So then I get the density function here and I get it there. So then we get this thing over here. Then another time I can realize that this is an integral of a sum. That's a sum of integrals. So therefore we're going to get two integrals, this one and that one that we have over there. And then I should realize that again, even though I integrate here over, say, the full support of y, I should realize, of course, that, well, this thing is only different from 0 at the moment that y is larger than q tau, than the quantile. So therefore I can here integrate from the quantile until the supremum support. Well, here I can do it the other way around, realizing that this is only different from 0 at the moment that y is smaller than the quantile. So therefore, then we're going to integrate from the infimum up till the quantile that we have over there. So therefore, in total, what we're going to get is this thing that we have over here. And then the next step that we can take is that we now can realize that what we want to do now is to, well, get the primitive of this density function that we have over here. We would like to now calculate the integrals. But that's just, well, the density function. We get, of course, the distribution function. Here we get a distribution function, but we get it there as well. So therefore, we can simply write it like that. Well, then I have to, well, evaluate the distribution function here in its supremum. That's, of course, simply equal to 1, minus the distribution function evaluated in the quantile. So that's this thing now that we have over here. And here we are going to get the distribution function evaluated in the quantile minus the distribution function evaluated in its infimum, and that's of course simply equal to 0. So therefore in total what we're going to get are all these terms now that we have over here. Now I can take another trick. And that is that what I do here is that I evaluate the distribution function of y1 in its own quantile. What is that? Well, that's by definition equal to tau, because of the fact that the quantile has its definition that at the moment that we're going to, well, evaluate any kind of distribution function in its own quantile, it actually gives us just the tau that we have over here. So this is tau, and that is tau as well. So in total what we're going to get is now this interval that we have over here. Well, now the first thing I'm going to do is that I multiply here actually 2 times by tau. So I can take tau out of the parentheses. So we simply get here 1 minus tau squared. Here I get tau multiplied by 1 minus tau. So in total we get this thing over here. I can also take the 1 minus tau out of the parentheses. Then I simply get tau here, and I get 1 minus tau there. So in total we're going to get then this. The taus here are going to cancel to each other. So therefore in the end I'm simply going to get tau multiplied by 1 minus tau. What does this mean? Well, to recap the things that we have so far, we should realize now that what we have is that we started here by saying that we would like to get the asymptotic distribution here of this numerator that we have over here. And we now know it. It's a normal distribution with a mean equal to 0 and a variance equal to tau multiplied by 1 minus tau. But what about the denominator that we have over here? Well, for the denominator we can be a little bit quicker, and that is that we should realize that this denominator, of course, it's a sample mean, and therefore it's going to converge in probability to its corresponding population mean. That means, of course, no summation but expectation. We're going to take the expectation of the, say, second order derivative of this thing we have over here, of course, so not over all the observations, but just the first observation, and we no longer divide by n as we do over here. So therefore we can realize that this, say, denominator is going to converge in probability. Well, I have to now scroll forwards, but it's going to converge to essentially this thing that we have over here. Then the question arises, what is that? Well, we actually know that the first order derivative, this is the second order derivative of course, but the first order derivative, well, we actually already know that. Even though we have been looking at the, say, first order derivative with respect to this mean that we have over here, that's exactly the same as taking the mean of the first order derivative, or at least under very general conditions we do know that the mean of a derivative is equal to the derivative of the mean. So therefore, question arises, what is this thing over here? Well, we already know that, because when we were looking at the, at the consistency of our quantile estimator, then we actually needed that at a particular moment in time. We actually already know that that's equal to tau minus the distribution function evaluating Q. So this thing that we have over here. Well, then the next thing that we can do is that we can look at the second order derivative. That's of course the first order derivative of this thing over here, or maybe better to say the mean of the second order derivative is equal to the second order derivative of the mean. This is the first order derivative, so it's going to be the first order derivative of this thing over here. That's not that difficult, of course. Then what we're going to get is, well, we simply are going to get the density function evaluated now in Q. So therefore in total what we're going to get is this thing over here. In particular we would like to look at this not in a general cube, but we only want to do this in the quantile. So therefore what we're going to get now is this thing that we have over here. So therefore another time to remember, what we now have is essentially everything. We're starting with this thing over here. Now we do know that this numerator is going to converge towards a normal distribution with a mean equal to 0 and a variance equal to tau multiplied by 1 minus tau. And this thing is now going to converge to, the denominator is going to converge in probability to, well, the thing that we have just derived. So that means that the numerator divided by the denominator is going to converge to also a normal distribution with a mean equal to 0 and a variance equal to the variance of the numerator, that's tau multiplied by 1 minus tau, divided by, where this thing is going to converge to, but squared. Take into account that for variances we always square it. So therefore what we're going to get in total is exactly what we have at the next slide. This slide that we have over here. Here I say it another time, the variance is going to be equal to the variance of the numerator divided by the variance of the denominator, or what a denominator is going to converge to, but squared. And therefore in total what we're going to get is tau multiplied by 1 minus tau divided by this thing squared. So this is relatively simple. The question of course arises, however, are we able to calculate this? Well, the answer to that is of course not. And the reason for that, well, there are two of them. First of all, we do not know what this quantile is, but what we can do. So we can replace of course this quantile with respect to its estimator. But what about this density estimator or this density that we have over here? We have no idea how it actually looks like. So the question arises, how are we able to estimate that density? Well, we can estimate that density in two ways. First of all, what we could do is that we could use a parametric form. So what we could assume is that this has a particular parametric form, for example, the normal distribution. Then, based on maximum likelihood, we can of course estimate the parameters of that parametric form. So for the normal distribution, the mean and the variance. And then we can simply substitute that into this density function that we have over here. That, however, has one problem, and that is that at the moment that the parametric form that we're going to assume is not correct, well then at least this estimator is going to be incorrect as well if we're going to use it. So therefore, well, one thing that you might of course say like, well, but this is only the estimator's variance. But that's of course not really a good thing to say at the moment that you're going to think in terms of statistics. So therefore, there is an alternative. And the alternative is that we're going to use a kernel density estimator. In case that we have a kernel density estimator, then we do not have to make any assumption with respect to density. We just estimate it non-parametrically. I would like to go on now with an application of the things that we have done so far, and I'm going to do that with respect to the Family Expenditure Survey in the United Kingdom. This is a repeated cross-section of about 10 to 12,000 individuals each year, depending on the year of course, and well, one thing which is not that nice with respect to this particular application is that the Family Expenditure Survey is actually quite old. It started in 1978, which is, well, probably even not that old compared to some other, say, surveys, such as the current population survey from the United States. But it did end actually already in 2000. So, well, the last information that we actually have is from 2000. Well, this Family Expenditure Survey is actually quite famous, and one of the reasons why is because of the fact that it has been used many, many times by Richard Blundell, one of the most famous labor economists, at least from Europe. It has detailed variables on consumption and the labor market. And what we're going to do here is that we're going to look at the distribution of wages among women and men. More in particular, what I'm going to do is that I'm going to look at the quantiles of the wages of women and men. So therefore, what I'm going to do over here is that I actually put here on the x-axis, I put here the, well, different values with respect to tau. They're in between 0 and 1, of course. And then on the y-axis, I will put there the quantiles. It's going to be the quantiles of the log hourly wage. So that's the reason why it's not that high over here. The maximum that we have here is around 3. So that means, well, 3 log, say, well, that means, of course, that the hourly wage is going to be equal to the exponential 3 in pounds at that period of time. So that's the reason why this is not that high. But what we're going to see is that we are going to do this first of all with women. The solid line is for women, and we have for men, we have the dashed line. We see a couple of interesting things. The first thing that we're going to see is not that surprising, and that is that the quantiles are, both for men and women, they're upward sloping. Well, that has to be the case. But another thing that we see, and probably also not that surprising, is that the quantiles for the men, they were always higher than the quantiles of the women. However, one thing that we can also see over here is that this is not that informative because of the fact that we do see that there is a difference, but it's difficult to see whether the difference, for example, here at 0.8 is that much different from, for example, here at 0.3. So therefore, it may be nicer to look at another picture. We simply are going to take the difference of these two figures that we have over here and that I have at the next slide. So here again, we have here on the x-axis different values of tau, but now I simply have looked at the difference between the two different curves that we had over here. And we get this picture that we have over here. From this we can draw a couple of conclusions. First of all, we can say that there is quite a big difference between, say, the quantiles of the women and men, actually over the whole distribution. And this difference is pretty large. It's, well, in most cases, more than 0.3, and take into account that we look here at log terms, so that means that it's, say, over 30%. Well, you should realize that this is, of course, very large. Bit difficult to say whether that actually depends on the time period that we use. So we use 1978 up till 2000. It's also difficult to say whether it might be maybe be related to some of the differences in characteristics between women and men. But this, of course, is a huge wage gap, as we see it over here. Probably now it's smaller than this 30% that we have over here in the United Kingdom, but well, it's, I would say, surprisingly large. Another thing that we can actually say is that there are differences with respect to the wage gap. We see here actually that it's not that high here really at the very bottom. It increases quite sharply, and we see that around, say, 30–35% it is going to be highest, and then it's going to drop. Well, it's not that much maybe, but it drops from 34% to around 26%. It has a sharp increase here at the end, but that could be explained by the fact that generally, at the moment that we're going to look at quantiles, the standard errors, they are largest around the, say, bottom and the top of the distribution. So actually here at the bottom and the top of the distribution, there they are the largest. So therefore, maybe it's better not to look too much at this picture that we see over here and focus more at, say, the general picture that we have until, say, 0.9 or something like that. What can we conclude from that? Well, one thing that you always hear quite often with respect to gender differences, apart of course from the, well, overall wage gap, people also talk a lot in the, say, policy debate about the so-called class ceiling. The idea behind the class ceiling is that, well, maybe the wage gap between women and men is not that large, but we are going to see that it becomes extremely large at the top. That is what a lot of people say. And the question, of course, arises whether that's true in general at the moment that we're going to look at this picture that we see over here, at least for the United Kingdom in the period 1978 up till 2000. Well, what we're going to see is that there's not that much support for a, say, a class ceiling effect. What we do see, apart from this very high top that over here, which I already explained, what we do see is, first of all, the wage gap is actually quite large overall. And what we also see is that it's actually largest here, more or less at the bottom of the distribution, and it becomes actually smaller at the top. So that means that this implies that there is no wage gap at all. The wage gap is quite large, but this seems to imply that there doesn't seem to be really a class ceiling in the United Kingdom. And that's actually what you see generally in many, many countries, that the class ceiling effect is not that large, but that it seems to be the case that in many situations, the, say, wage gap is actually larger at the bottom as it is at the top of the distribution.